Okay, so we shall start our discussion. Around 36 participants available in this session. So this course is about tensor mathematics and constitutive modeling. So before starting the course, let me tell you something that you must have a notebook and pen with you because it is a mathematical course, and it's better to while discussing you should also take a notes. I will share the blackboard and I will write. I will do all this the blackboard thing as we are doing in the classroom, and this way we will have our discussion. So first I want to get familiar with at least 2 or 3 students so that the our conversation will relatively go easier way. So I'd like to ask Amit Kumar. Can you just unmute and have a little chat with me? Yeah, Amit.
Yes, sir.
So you can see me as well as you can hear me, isn't it?
Sure, sir.
Okay. So the way how I told you that how the class will go, that I will share my screen and then you will see the blackboard. I will write on the blackboard, and then it's whatever I will write, you guys should also have the pen and copy with you so that you can write and take notes.
Yes, I'm ready
Whenever,
with that, actually.
yeah, will it be good?
Yes, it is good, sir, because I know that tensor mathematics involves mathematics.
Yeah, and as well as after 20 minutes or 25 minutes I would like to have some discussion so that it's the discussion will not go in a passive mode, isn't it?
Okay.
So so making the discussion or whole conversation in a very active mode in during this whole session. In between 20 after 20 minutes or 30 minutes we will have a small break kind of thing where we can discuss or clarify our queries.
So one thing
Fine?
we can do, if
Yes.
you permit, then 5 minutes gap so that we can straight our legs because it's a long session.
Sure,
You-
sure, sure, sure,
Okay.
sure. So now I'm going to start the discussion. So what I'm doing, I'm sharing the screen, and Amit, you can unmute yourself so that you can tell me that whether you are able to see the screen or not. Okay.
Okay, sir. Okay.
Huh. So this is tensor
Blackboard.
mathematics
Yes, yes,
black one.
yes, yes.
Okay. I think so. Let's start the discussion. So this course is about the tensor mathematics in constitutive modeling. So there are two words used in this. One is the tensor mathematics, another is the constitutive modeling. Before going to discuss what is tensor mathematics, what is constitutive modeling, first I'd like to discuss about the mechanics, what you have studied in your 11th standard as well as first year of engineering. If you are engineering student, then you have studied the mechanics course in your second year of engineering, and even if you are master student, then you must have done the mechanics of solid or mechanics of fluid in your master course. So you are familiar with what is mechanics. So let's start the discussion with mechanics, and then I will go that where we are going to use the tensor mathematics and what is this constitutive modeling is. So as we know that this mechanics, we have started our journey of this mechanics from very simpler one, and that is mechanics of rigid body. Mechanics of rigid body. So from here we have started our journey of studying the mechanics, and if you recall that you have seen the various physical quantities in this course, and these physical quantities are mass, density. Okay, so these, if you see, these are the physical quantity, mass and density. You are familiar with this. Then you also have seen that the displacement, then you have seen the velocity, you have seen position vector, and acceleration, and so on. So these are the quantity you studied when you have studied the mechanics of rigid body. And these are the, if you see, these are the effect what you are observing, and you are trying to understand what is the cause of this. Then you have come to the conclusion that the cause must be the force, momentum, angular momentum, and torque. So these effect, and you try to understand, then you find that this is the cause, and you try to relate this. So we are observing the effect, and we are trying to get that what is the cause behind it, and we have the force as well as displacement, we have the force, acceleration, and so on. And a very famous equation, if you remember, that is F is equal to ma. That is what this is, relating the cause and effect. And this is very famous equation, everyone of us must know this. So if you see, the whatever the physical quantity we have seen in the mechanics of rigid body, all this physical quantity, either the scalar, okay, like example is mass and density, or vector, and the examples are many. These are displacement, your force, acceleration, velocity, all are the vector quantity. So these physical quantity are the vector quantity. Fine. And also we have studied various natural law, like the conservation of mass, where we must satisfy the continuity equation, because whatever the cause and effect relationship we are establishing, that must satisfy the law of nature. So we have studied the conservation of mass, we have studied the conservation of energy, we have studied the thermodynamics principle, and so on. Angular conservation of angular momentum, conservation of momentum, and so on. So this is what, during our journey of mechanics of rigid body, we get familiar with all these physical quantity. And most of the physical quantity, if you see, that either it is scalar, mass, density, even in the physics, temperature and all, or vector, displacement, force, velocity, angular momentum, momentum, torque, etc. Now, after this, you have also studied the mechanics of deformable body. Mechanics of deformable body. So here, and the very first course you have done, that is either strength of material or mechanics of solid in your second year of engineering. So this mechanics of deformable body, here we are studying that if force is applied on any body, then it will get deformed, it may fail. So why it is happening, how the force applied on its surface is being transmitted within, and which causes the deformation throughout the domain, as well as at some location it may fail. So these things we have studied in mechanics of deformable body. And the two very important physical quantity we get familiar with, that is stress, and another is strain. Now let's see what is this stress is. So generally it is denoted by the sigma. And if physical meaning or geometrical meaning, if you want to see, in xy coordinate system, you are considering a cuboid, and with respect to that, if this is x, this is y, this is z, then this is sigma xx, this you have sigma xy, this is sigma xz. Here tau xy also being used, or sigma xy. So both sign or both notation are being used for this. Sigma yy, sigma by z, sigma, this is yx, sigma zz, then we have sigma zy, and sigma zx. So if you see, we have 9 component of a stress. Okay, and these 9 component, if you are putting it in the matrix form, in general stress condition, if you remember, then it is sigma xx. Let me write your familiar things what you have studied in your BTech. Xy, then xz, then you have tau by x, sigma by y, tau by z, tau on z plane, it is zx, z by, and sigma by y. Sorry, sigma zz, sigma zz. So we have this 9 components of a stress. If you remember, for a vector, we have 3 components in x by z axis, x by z plane, geometrical plane when we are considering. But in case of a stress, we are having 9 components. Now let's consider any this tau by x. Why? What these subscript represent? So if you see, this first subscript represent the plane on which this is acting. Okay, and the second subscript represent the direction of in which along which it is acting. So apart from the magnitude, we require 2 plane or the 2 directional sense. So this stress component having from the, we must define, in order to define the stress component for complete definition, we need the magnitude, then we need the direction of plane, and we also require direction of the force or the stress. So just try to compare with your vector quantity. Let's start with the scalar quantity. In case of a scalar, we actually, in order to define it completely, we only require magnitude. What is the magnitude? How much, let's say the, what is the temperature? So this much is the temperature. And the weight, then let's say the 5 kilogram, 2 kilogram, and so on. So we only require actually the magnitude to define the scalar quantity. In case of vector, apart from the magnitude, we have to also define in which direction it is acting. Otherwise, its definition is incomplete. Its description is incomplete. So we require the for a scalar we require only magnitude. For a vector quantity, we require, apart from the magnitude, a direction to indicate in which direction it is acting. Now, when we came to the stress, then in order to define a stress, we need magnitude, we need direction of a plane on which it is acting, we need a direction along which it is acting. So here we have the 2 directions. Okay, so see, the order of this physical quantity are increasing as we are moving from a scalar to vector, a scalar to the let's say here the stress, and this is generally defined as dyadics or second order tensor. Okay, similarly, your strain component is also a second order tensor. So when we are dealing the mechanics of deformable body, then our physical quantity is having the higher order than the vector quantity. So if I'm making it a general, so actually this tensor is a generic term. This tensor you will find it's a generic term, and even a scalar is also one kind of a tensor. So a scalar where only magnitude is required, this is 0th order tensor, because here only we require magnitude. When vector, only one direction apart from the magnitude, the one directional sense is required to define it completely, then it is first order tensor. Here the dyadics, or here example is a stress and a strain. Here Apart from the magnitude, we require two directional sense to define it completely. Then it is second order tensor. Okay. Do you know there is a fourth order tensor as well? The stiffness, which relate the stress and strain. Your the simpler one is modulus of elasticity. This is fourth order tensor. Why it is fourth order tensor? Because it is relating the second order tensor stress with the second order tensor strain. So then it must be a fourth order tensor. So four directional sense required, the two of the stress and another two of the strain. So this is what the tensor is, a generic term under which the whole scalar vector, dyadic stiffness, and the second order tensor, fourth order tensor, we are coming in under this umbrella. So we will start our discussion that so this is what the tensor is, and we must know, in order to study any subject, we must have a good idea about the mathematics of that subject required for that subject, because mathematics is a very perfect and precise language to describe that the content, the physical phenomena. So that's why it is very important, because we have to deal with the deformable body. So it is very important to understand that what is mathematics, what is the mathematics of the tensor, and that we will discuss in this course. So this is about the what is tensor, and what are the different type of tensor, what is the order of tensor, and so on. Now I will come to the constitutive modeling. What is this constitutive modeling? So as when you are applying a load on any body, some load you are applying on a body, then what will happen? Because of this load, you are observing that deformation is occurring. Okay, so this load applied on the surface, on the traction, on its the surface of this the domain, and you are observing that inside also some deformation is occurring, and that you are measuring in terms of a strain. So it means that force is being transmitted within each and every point of this domain, and that transmission of the external load we are actually defining by using a stress. Okay, now we are trying to relate that, okay, fine, we have observed that deformation is occurring when we are applying some external load on the surface. Is it okay? And now, is there any relation between these two? So the stress is what you are, and you have strain. So sigma and strain. Now if we are trying to find, does any relation exist between these two? So if I say in a very general term, this is strain what you are observing, because you are not observing stress, you cannot see a stress. So this is what effect you are observing, and you are trying to understand what is the cause of this, and this stress is the cause of the deformation. Okay, so we are making an inference that, okay, this load applied in this surface must transmit within the domain so that the deformation occurs. So this is the cause and this is the effect. When we are trying to find the relation between, and whole of our human intellect and scientific discovery, if you see very carefully, then you will find it is nothing but finding the cause effect relationship. So if something is happening, there must be some cause, and so we are trying to establish a cause effect relationship. In case of deformable body also, we are trying to establish the cause effect relationship. It means then sigma and strain relationship. This is what our objective is. Then only we can analyze the system. Okay, now this cause effect relationship for deformable body, this stress could be temperature also. If you will increase temperature, you will also find some deformation, some distortion in the body. So here for a discussion purpose, we are just focusing on the, let's say, stress and strain, but you can also understand that temperature could also deform or distort the system. So this relationship is known as constitutive modeling, the process by which we are establishing the cause-effect relationship for a deformable body is known as constitutive modeling. Okay, and as we know that this whole constitutive, the simpler one you have studied, that is Hooke's law. In any material, this is the first what we are studying, that sigma is equal to E epsilon. This is the simplest possible, the constitutive relationship for a deformable body. But as we know that material also behaves a very complex way. So all this non-linearity will also come into the picture. So this whole the constitutive modeling field is also very complex, and we have to understand the mechanical behavior very precisely, and then we have to try to find out the relation between the load applied, stress applied, and the deformation observed within the domain. And this relationship, the cause-effect relationship, also satisfies the law of nature, law of continuity, law of conservation, and all. So this is whole the science of constitutive modeling. Okay, just imagine that further. Let's, in any material, when you are applying some load and you are finding that it is failing at some angle, just imagine that we will start thinking that why it is failing at this point, what happened to this point, what is the reason because of which the failure occur along this plane. So we have to describe this, the cause. In order to interpret the cause, in order to inference the cause, we have to be deep knowledge of material behavior as well as the mathematical structure to define it. Otherwise we cannot succeed in this. So this is what the constitutive modeling. And since we are dealing with the second order tensor, fourth order tensor, so the knowledge of the tensor mathematics is very much important in this case. Okay, so after this I will start discussion on, first today we will discuss on the vector algebra, vector our fundamental knowledge of the vector, so that first we will get familiar of that, then we will move further to go for the various notation and the higher order tensor and so on. So before going to that, I would like to take some question. If you have, then please ask one by one. Param Singh, do you have any question?
No, sir.
Oh,
Sir,
no. Yes.
Sir, actually, you said that for this constitutive modeling, that
Yes.
is for only for deformation. So it
No,
could
no,
be
it
only.
is. Yeah. First you put your question. Yeah.
So it is for deformation only. My question was that only.
It's not only deformation actually. It's failure of the material is also part of the constitutive modeling.
So
Let's
if,
say,
so I am an experiment guy, and if I am doing some experiment and I'm getting some parameters for
okay.
that thing, so it is also applicable there.
See, whenever you are actually, whatever observation you are making, finally what we are doing, based on these observation, we are trying to get the mathematical relation out of which, isn't it?
Yes.
And the parameter is what? Parameter is the parameter defining this constitutive modeling.
Okay. Okay.
Isn't it? So
Got it.
when you are estimating or calibrating some parameter, it is related to some mathematical relation, that is constitutive modeling. Let's say Hooke's law also, when we are finding out the modulus of elasticity, this is a finding, calibrating a parameter of a simpler linear elastic constitutive relationship, isn't it?
Yes.
So whatever parameter you are estimating from experiment, that is nothing but the parameter calibrated for a given constitutive model.
Sure.
So,
Okay.
isn't it? Okay. Any other question?
Yes, sir. I am Parth. I am
Yeah.
from electrical engineering.
Okay.
So I wanted to ask a general doubt. Generally, whatever we discuss, isn't it called modeling, just modeling? Because we study systems like electric motors, and we try to predict the behavior. We give some inputs, and we try to predict what will be the output torque, the speed. So that we say as electrical model of the system. So is this term constitutive modeling specific, or it is just modeling?
So there are two things. See, one is system. System is made of many small constituents, various components. Let's
Okay.
say electrical machine. So it is not made of a single unit. Rather, it is a combination of various components. Each components will behave differently. So what you are talking, you are now telling about the whole system. But just
Yes.
imagine, each is the various components are also connected to make a system. So when we
Okay.
are studying each component and trying to understand how it behave, then we have to first model all these things also. We have to
Okay.
understand their individual behavior. Then only we can understand we can understand the system behavior.
Yes.
Similarly, in generally, this constitutive modeling term is used in material aspect in commonly, where the mainly if external force is applied, then
Okay.
how that material will behave. This so this is more about the deformation and the external load. It may be temperature, it may be the stress, it may be the some other forces. So because of that, what will happen to this in terms of deformation, in terms of failure, and so on. This is a general convention in the material modeling section, and that is termed as constitutive modeling. But the
Okay.
modeling, what you are talking, this is system modeling. This also, this we can say that mathematical modeling.
Okay. Fine.
Okay,
Understood.
okay, fine. So shall we move to the vector mathematics, if you allow?
Yes. Fine.
Okay, fine.